guess I'll begin with a story. Why not? You and your dog are walking in the woods. I'm no artist, believe me. And if you've seen this, don't give it away. Let's see, no, I want it the other way around. We got it, I think. And this, and then this, and something like that. And you're walking in the woods and you see this thing with your dog. And you say, what's that? And the thought suddenly hits your head that it's a bear climbing a tree. But you're not sure, you know. So you kind of edge around here, and it moves a bit. But you then decide to send your dog around, because if it is a bear, you know, you don't want to be around there. So you send your dog out there, and of course that's the worst thing you could have done, because the dog starts barking at the bear, and then the bear climbs down the tree very quickly at you, because you're the owner of the dog. This brief story is my caricature of William Whewell in the 19th century. And it's my caricature of William Whewell because Whewell says you got some phenomena here, right? Some puzzling phenomena, and you want to understand what's going on. You want to explain the phenomena. And so the first thing you'd have to do, which he called colligation, is to apply some concept that the mind supplies to explain what's going on here. So the concept you come up with maybe is bear climbing a tree. And that's the discovery stage of science, according to Whewell. But you're no scientist if you just, do that, if you just dream up a hypothesis, which is very difficult to do. In fact, Whewell thinks it's the most important part of science. The rest is more automatic, I think, for Whewell. But it's the great geniuses who think up the bear and the tree hypotheses. I mean, his example was not, of course, it was Kepler thinking up the elliptical orbit for Mars. Well, a similar thing. And the next stage is, that's the discovery stage, he called it. The next stage is testing. And testing consists in, doing the things that you ordinarily would think, showing what this thing can explain, making predictions. So your prediction is maybe that if you send the dog around there, he'll come running back and say, yes, it's a bear. Of course, you don't expect the bear to come running back either, but that's what happened. And this is the way you test. And the more varied the phenomena that you can predict and explain, so on, what he calls consilience, the more tested the theory is until it becomes absolute certainty. So this is a simplification, a caricature perhaps, of William Whewell. How many of you have read Hempel's book on philosophy of natural science? It's a very famous old textbook. And do you remember what he began with? A similar example, except this is from Ignaz Semmelweis. Remember who was a doctor in Vienna in the mid-19th century. Okay? And Semmelweis was at the Vienna General Hospital dealing with the following problem, that there were two maternity wards in the hospital. And one, the women had a much higher incidence of what was called childbed fever, and were dying from it at that time. And Semmelweis had to do what Whewell described as, making up various hypotheses. In other words, conceptualizing the data in different ways. And Semmelweis actually struggled quite a bit, because he had one hypothesis that in one ward the priest walked to give the last rites to a dying patient, which was psychologically very damaging to the women in that maternity ward, and hence was causing their childbed fever. until he finally hit on and then he tested that by preventing the priest from walking there, but the incidence of childbed fever remained the same in the more infected ward. And so finally, the story goes that he thought of the hypothesis that, well, what's happening in this case is that the medical students who are doing autopsies are doing autopsies just before they went into the first ward, but not the second. And it's the infectious material that they were carrying without washing their hands properly. It's infectious material they were carrying which is causing this. And so he tested that, did the consilience and prediction thing and so on, and that turned out to be right. And so Hempel says, just like Whewell, there are two stages to scientific inquiry. The first is the discovery stage, and the second is the testing stage, and that's what science is all about. Now, my second story pertains to the early 1980s when Steven Weinberg, Nobel winner, of course, in physics, came to Johns Hopkins to give the Brickwitty lecture. And I attended it. And Weinberg, it was more autobiographical than anything else. He talked about string theory. And he wanted to explain, what he was doing, why he went into string theory. He said that was a hot theory at the time, it still is to some extent. He took a year off to learn the math necessary to participate in string theory. He talked as if he was just very excited about his work in string theory. And of course he wrote a book about this, a popular book, Dreams of a Final Theory. And he said it would be 50 to 100 years before the theory could be tested. The energies required would be much too high, but nevertheless it was worth doing. And more recently, well, I should say what happened at the end. In the discussion period, it was amazing to me because this was a lecture for physicists. And there was a tremendous division between two kinds of physicists. One, the theoretical physicists said, yeah, this is interesting stuff. The experimentalists were down on him in a very difficult way, saying that this is not physics, it's not science, it's metaphysics. You can't test the darn thing, and you don't even know how to test it. What would test it? So you've got Whewell's, perhaps some of Whewell's, colligation stage or Hempel's discovery stage, but nothing of the testing stage, and that's what we do in philosophy. So I was very taken with this, and Weinberg didn't seem to mind. He won the Nobel Prize. He did his physics, and he didn't seem to mind. I wondered why he didn't seem to mind. The same thing with Brian Greene, who came last year to Hopkins to give a special lecture on string theory, in which he was much more descriptive of what string theory was doing and the problems and so on. And he put up on the board, various problems, one of which was there's no test for the theory at all. And there won't be one. Similar thing, and he didn't seem to be worried about it. And the guy sitting next to me was a graduate student in physics, and he said, we don't teach string theory in our department because it's philosophy, not physics. And I was really taken with that. All right, that's the end of my stories, and I want to start with Maxwell now, because Maxwell, in the 19th century, was interested in various problems, obviously. In 1855, Maxwell wrote a paper called On Faraday's Lines of Force. Probably his first major great paper. It's a big one. I think it's 72 pages, something like that. And I'm going to quote some things. I'm going to quote some things from my book, but not the things that I wrote, the things that Maxwell wrote. The question that Maxwell was raising in this paper, as in several other papers he wrote later, both in electricity and on molecular kinetic theory. The question was this for Maxwell: what do you do if you don't have a theory to explain the phenomena? Or even if you have a theory, but you can't prove it, what do you do? Well, if he had read Descartes, Descartes' Problems of Philosophy, Descartes says at a point, if you can't intuit the correct answer, or if you can't deduce the answer to your problem from the intuitions that you start with, then you don't go any further. You turn to another problem where you can solve it. And Newton effectively said the same thing. Of course, he rejected Cartesian intuitions and so forth. But Newton said, his official doctrine, though he violated it many times, his official doctrine was that, look, hypotheses have no place in experimental philosophy. Right? That was what he says, and hypotheses are propositions that you cannot deduce from the phenomena, that you cannot derive from the phenomena using his 4 rules plus, mathematics. And so you don't speculate at all. You don't do that. And of course, Newton did it, but that was his official doctrine. Now, Maxwell, I think, was more interesting in these regards than Whewell or Hempel. And Maxwell said, look, there are lots of things you can do, even if you don't have a theory. And he began with certain well-known phenomena in electricity and magnetism. And what he said in 1855 on the paper on Faraday's lines of force is, I'm not going to present any theory in this paper. I don't have one. Nobody has one. I mean, nobody has one that I'm interested in. Yet I'm going to do something with regard to the known facts, to the phenomena, to the data. I'm going to make them understandable to you in a certain way, without speculating, without hypotheses. And how's he going to do that? That's the question. So let me quote from Maxwell, 131 here. He says, toward the beginning of his paper, he says, the first process, therefore, in the effectual study of the science must be one of simplification and reduction of the results of previous investigation to a form in which the mind can grasp them. The results of this simplification may take the form of a purely mathematical formula, where you have a formula in which you don't indicate what the symbols really mean, physically speaking. Or the alternative is between this purely mathematical way of looking at things and what he calls a physical hypothesis. In the first case, we entirely lose sight of the phenomena to be explained, and though we may trace out the consequences of given laws, we can never obtain more extended views of the connections of the subject. If, on the other hand, we adopt a physical hypothesis, we see the phenomena only through a medium and are liable to that blindness to facts and rashness and assumption which a partial explanation encourages. We must therefore discover some method of investigation which allows the mind at every step to lay hold of a clear physical conception without being committed to any theory founded on the physical science from which that conception is borrowed, so that it is neither drawn aside from the subject in pursuit of analytical subtleties that's the mathematical thing, nor carried beyond the truth by a favorite hypothesis. In order to obtain physical ideas without adopting a physical theory, we must make ourselves familiar with the existence of physical analogies, which is what he's going to do in this paper. By the way, when I started getting interested in Maxwell in the late 1980s, I went to the University Library at Cambridge University, and I was told that all of Maxwell's correspondence are in about 6 or 7 or 8 shoe boxes. Which shoe box did I want? And I said, I don't know, give me them all. And so they really spent quite a time loading them on a big car. These were big things. And I started going through his correspondence. Now, of course, this was in the day before the typewriter, so it's all handwritten stuff. And it's all, mid-19th century stuff on, acid-filled paper. Okay, so it's falling apart. They did not demand that I use gloves, and the only request they made is don't use a pen, but I could use a pencil. Okay, and I was amazed. I could get this far, but I did, and I came across a letter written to Maxwell. I forget what year it was, in the 1860s. Early, and I think he was a professor at the University of London at that time. And the letter was written by some, I guess we might call him a dean or something at Cambridge University. And it said, "Dear Maxwell," the first paragraph was, "We are establishing the Cavendish Laboratory at Cambridge University, and we are establishing the Cavendish Professorship at the Cambridge University." This is the kind of letter you love to get. Paragraph number 2, "We have offered this position to Lord Kelvin, who has thought about it but declined." Number 3, "Would you be interested in this new position?"
Can you suggest someone else?
What? yeah, that's a good one. And so, and Maxwell was not amused by this. I mean, Kelvin was a good friend of his, perhaps the senior man, but Maxwell was the true genius. And Maxwell wrote back very coldly. He didn't even thank this functionary for writing the letter. His main question was, how much teaching will I have to do? See how we live in the modern age here. And of course he did take the job. He was the first Cavendish professor of physics at Cambridge. But his life was very short, so he didn't last a long time there. Now, Maxwell then says, look, what I'm going to do in this paper is try to help you understand some of the known laws of electricity and magnetism. I'll try to organize them in a certain way. And I'm going to subject this to 3 conditions that you will have to, I will try to abide by. And he does this in this paper, and I'm going to talk about 2 more papers where he develops 2 other methods of proceeding. This he calls the method of physical analogy. And the first idea is that it's got to be physical. You've got to give me a physical picture of what's going on. The second idea is that you've got to spell it out. Not just give me a few ideas. Maxwell was asked to write an article on molecules for the Encyclopedia Britannica. And there he's writing for a more general public, and he says, let me give you an analogy between molecules in a gas and a swarm of bees. Think about that. Now, he didn't spell this out, but he didn't need to. Okay, the bees are roving around, in a enclosed space, and that's the way the molecules are doing and so on. But in this paper, no, he's doing real physics, he thinks, and he wants to spell this whole thing out so that you'll get a thorough idea of what's going on. And the third thing, he wants to express it mathematically, but the mathematical things, the equations that he introduces, will all have a physical interpretation that he makes very clear. So what does he do? he says, and he wants to make sure it's an analogy which you don't know about. Okay. In fact, it's an imaginary thing. He constructs what he calls an imaginary fluid flowing through tubes. And the imaginary fluid is the analog of the electric current. Okay. And then he starts with Faraday's lines of force, which you've seen, around a magnet. But that's not three-dimensional. So he wants to give you a three-dimensional thing with tubes. And you can vary the thickness of the tube and thereby vary the velocity of the tube. And the velocity of the fluid will represent the magnitude of the force, the electrical force. And he sets it up this way. He sets it up so that on the one side you have the electric field. Here's the electric force at a point in the field is represented by the velocity of fluid at a point in the fluid. And a particle of positive electricity is represented by a source of this imaginary fluid. And the electrical potential at a point is the pressure of the fluid at a point. And then he sets it up so that Coulomb's law of attraction among forces, it's an inverse square law, will be satisfied in the fluid as well. Then he works out all kinds of consequences, mathematical consequences, some of which are interesting to this thing, and he does this for 72 pages. Okay, and he actually works out some solutions for in the case of the fluid, what's going to happen, and you can apply that to the electric field if you like, and this gives you an understanding, he thought, of what's going on in electricity. Well, how? How does it do that? How does it do that? Look, one way to understand, here are the data right here. See? And one way to understand these data is to conceptualize them, like Whewell said, to organize them into a bear. I mean, it doesn't mean your hypothesis is true. It's just one way to understand the thing, which you then have to test. Okay. And that's what Whewell says we do all the time, and Maxwell agrees that, I can conceptualize the data in various ways. Doesn't mean I'm doing it correctly or that it'll lead to something interesting, but this is one way of doing it. One way of conceptualizing the data is the way we did it here, say, well, it's a bear. Another way to conceptualize the data, and that's the route that Maxwell takes, is to use an analogy. Saying, well, it's like this. So that's his bee analogy. The swarm of bees is like what it is to be a gas composed of molecules swarming around. Okay? That's another way of understanding things, and that's the route Maxwell takes. And he thinks that by drawing this analogy, you will be helped in understanding, in this case, the real known experimental laws of electricity. And as I say, he obviously takes this very seriously because he spends 72 pages on it. Okay. So this provides a physical way of understanding the phenomena, and this is the crucial point for Maxwell, a physical way of understanding the phenomena without knowing what's causing the phenomena. He is not presenting to you what you would call a theory of electricity, of whether electricity really is a fluid of some kind, whether it's composed of particles of some kind. He's not playing that game. He's just saying, I can organize the data in this way, and this may help you, understand these laws. Okay. There are other advantages that Maxwell, let me see if I can, if there's any other. Yeah, so he spends some time trying to admit to you, tell you that this is not a physical hypothesis. He is not, this is a purely imaginary fluid which he's constructing in his mind for the purposes of the paper. There's no, you don't know any more about what's causing electricity after you read the paper than you did before. Okay. Now, he also says that there are some advantages in using this method besides sort of giving you a nice understanding of things as a physicist. It's useful in teaching, Maxwell. He talks not only about analogies, but drawing pictures. Okay? And he conceives of this all as part of being a scientist. This is part of the scientific pursuit. Now, finally, something he doesn't emphasize in this paper, and I think I know why, is that you may sometimes be in a situation where you can make analogical inferences between the analogy that you constructed and the real thing, of which it is an analogy. You can say, okay, this holds in the analogical system, perhaps it holds in the real system as well. But then you'd have to have a close connection between the two systems. You'd have to be convinced that the analog system really does exist to make an analogical inference to what's going on in the real system. But Maxwell doesn't want to do that because he's dealing with an imaginary analog, not a real one. Okay, so that's the first paper I want to just mention briefly. If you had told Maxwell this is not scientific pursuit, he would laugh at you. This is important part of what he regarded as being reasonable science. The second paper I want to talk about was written in 1860. And he called it Illustrations of the Dynamical Theory of Gases. And now it's changed the subject to a discussion of why gases, why gases behave the way they do. In 1860, the various gas laws were known by physicists, and Maxwell said, "Look, these laws, we want to know why they hold." So his question was different from the electrical case. He didn't want to speculate in the electrical case. He wanted to speculate, however, in the molecular case. And he says so many of the known properties of gases can be explained using the hypothesis that gases are composed of minute particles, which he sometimes called particles, sometimes called molecules. That it becomes a subject of rational curiosity, I think those are his words, as to what's going on in these gases. Okay. So he says, look, I'm going to introduce some assumptions about molecules inside gases. And the assumptions were, in 1860, the assumptions were that the gases are composed of molecules which are in motion, tiny little things you can't see, and that these molecules interacted only at impact. There's no action at distance here, or when they hit the sides of the container. Okay, and they obey Newton's laws of motion. Okay, and furthermore, they're spherical. And furthermore, they collide when they do elastically, so no energy is lost. Okay. So he says, I'm going to work out this theory now. He calls it, unfortunately, I think, he calls it a physical analogy, just like he did in the electrical paper. But it's very different from the first paper in 1855. It's very different because Maxwell is actually supposing these things exist inside gases. That's a supposition, and he's going to use that supposition to explain why gases behave the way they do. And that is not the case in the electrical paper. He's not saying here's why electricity works the way it does because it's composed of a fluid. Not a bit. Okay, so he works out various, using mathematics, he works out various results, which he puts in the form of problems to solve, in effect. And one problem to solve is how, roughly on the average, how far a gas molecule goes before it hits another one, called mean free path. And he worked out a general formula for this. His most important result in the paper, which bears his name, anybody know?
Displacement current?
What?
The displacement current?
No, not that. That's in electricity.
Maxwell distribution.
Maxwell distribution law. He was interested in the distribution of molecular velocities inside of a gas. And so he made all kinds of assumptions. And he didn't justify any of them. Okay. Remember what I said at the beginning? He said so many of the properties of gases can be explained by the assumption that they consist of molecules. But, okay, so what? That doesn't mean there are molecules. That doesn't mean there probably are. It just means that, hey, here's a theory, that could, if it were true, explain these things, some of these things. So he then derives this law, which took his name, Maxwell distribution law of molecular velocities. And it is quite it's still taught today in, physics courses. Maxwell Boltzmann improved on it and so on. But if you said to Maxwell, hey, Maxwell, now keep in mind Weinberg, if you said to Maxwell in 1860, how do you know that's true? He would have said, I don't know it's true. In fact, if you had said to Maxwell, what would verify that statement, this interesting law that you've introduced, he would have said, no, I don't know. Actually, it wasn't, remember, 1860, it wasn't until 1927 that molecular beam experiments were done, which confirmed, generally speaking, Maxwell's distribution law. Okay. So Maxwell writes a letter, this was just before he published the paper, but he published an abstract of it. He writes a paper to Stokes in 1859. He says, well, here I've gotten some interesting results from molecular assumptions, even when I don't even know if there are any molecules. Okay. What do you think about that? Okay. So, what was he trying to do? What's the point of all this? Well, I think the point of this was to say, look, I've got a problem. I'm a mechanical philosopher. I believe, the world consists of particles in motion subject to Newtonian laws and so on. And it would be very nice if I could use these assumptions to explain how gases behave. But how will I do this? I don't know. I have to work it out. In other words, the problem for Maxwell in 1860 is this problem. How is it possible to explain gaseous phenomena? The known laws, Boyle's law, the ideal gas law, Gay-Lussac's law, and so on. How is it possible to explain these known phenomena using mechanical assumptions, which presupposes the question, is it possible? All right. So, in the end, at the end of this paper, Maxwell says, well, I've done some of this stuff. It's really, it's amazing, okay? But I've got some problems with the thing. First, I can't explain, my theory is inconsistent with certain known results. It's inconsistent with the ratio of specific heats of gases. It's too far off. It gives you a prediction that's too far off for Maxwell. And that was his deepest worry. Another worry was he can't explain why gases conduct electricity when they do. Okay? He couldn't do that. And he didn't try. So he called this part where he's mentioning all the problems he has, hitherto unconquered difficulties. I like that expression, hitherto unconquered difficulty. But he never said, uh-oh, my theory is refuted, the way Popper would have. I mean, he's got a conjecture up here and a refutation with the fact that the specific heat ratio is well off. Okay. No, Maxwell did what, of course, physicists will do and said, okay, these are problems. I can't solve them all. I've got some interesting results here. I don't know whether they're true. That is, I don't know whether my assumptions are true. He made all kinds of assumptions, not just at the beginning of the paper, but throughout the paper, to build up certain answers to the questions he was raising. And if you had asked him, how do you know that's so, Maxwell, he would have said, I don't. But it's a simple assumption to make. Let's see what happens. His paper satisfied his three desires. He's giving you an understanding of something. But it's not an understanding of how gases in fact behave, but it's an understanding of how they could behave if they were purely mechanical. It's the same thing, put it very simply, but with an analogy. The detective tries to solve the crime, and the detective says, well, let's see whether the butler did it. Okay. Well, then the first question is, well, how could the butler have done it? I mean, the master of the house was much stronger than the butler. The master of the house was strangled. How would the butler get up there to strangle him? So he works out a theory. Not that the butler did it, but this is how it could have been done. Okay. Defense lawyers simply do this quite a bit when they defend their clients. Well, this is how it could have been done by someone else, not my client. Okay. A perfectly legitimate way to proceed, and exactly the way Maxwell did proceed, but again, you have to look carefully at what he was trying to explain, that is, how gases could behave mechanically and give you some of the known results we get. Okay. Finally, let me turn to the third paper, which is, in some ways, the most interesting. It is a paper written in 1875, and it's called On the Dynamical Evidence of the Molecular Constitution of Bodies. Okay. And 1875. So the first paper was 1855, the next paper was 1860, and now it's 15 years later, 1875. And Maxwell, of course, is Maxwell, and he's become very, very famous, and the first Cavendish professor, and so on. And he really does believe there are molecules by this time. And he's writing articles, again, for the Encyclopedia Britannica, in which he says, here's why I'm justified in believing there are molecules. But in this paper of 1875, he says, let's see if I have any juicy quotes for you here. 157. We have, he says toward the beginning of the paper, in attempting the extension of dynamical methods to the explanation of chemical phenomena, there's a gas law, we have to form an idea of the configuration and motion of a number of material systems, each of which is so small that it cannot be directly observed. We have, in fact, to determine from the observed external actions of an unseen piece of machinery and its internal construction. Okay. And then he waxes philosophical. That is one of the reasons I really like Maxwell, because he's not afraid to tell you in philosophical terms what he's up to. The method which has been for the most part employed in conducting such inquiries is that of forming a hypothesis and calculating what would happen if the hypothesis were true. If these results agree with actual phenomena, the hypothesis is said to be verified, so long at least as someone else does not invent another hypothesis which agrees still better with the phenomena. So Maxwell is rejecting what is known as the hypothetico-deductive method. Have your hypothesis, deduce some results from it. Same thing that Hempel was talking about in philosophy of natural science, the Semmelweis hypothesis, deduce consequences, go out and test them, and if they test right, then you're probably right. No. He says he's going to introduce a new method. So the first method was the method of physical analogy. The second method, which I call, using his term, an exercise in mechanics. And the third method, he himself calls a method of physical speculation. He says, when examples of this method of physical speculation have been properly set forth and explained, we shall have fewer complaints of the looseness of reasoning of men of science, and the method of inductive philosophy will no longer be derided as mere guesswork. Okay, well, Maxwell doesn't spell out what the method is. You have to read the paper to see what he does. And what he does is interesting. Unlike the other two papers, the other two methods, he starts by giving you some reason for thinking that gases, he's interested in that, may be composed of molecules. Okay? And he talks about various experiments that have been done, though he doesn't tell you anything about them. There were experiments done in the middle of, at the end of the 18th century and, to disconfirm the caloric theory of heat, where heat is a substance. And there were, so heat is a substance or it's not. And if it's not, what is it? Well, in the middle of the 19th century, there were experiments done to show that heat is connected with work, mechanical work or energy. Okay? So Maxwell thinks that these experiments done by Joule show that that heat must be a form of energy. And he wrote a book, Maxwell wrote a book called Theory of Heat, and in which he goes and tells you something about this. He says, well, there's two kinds of energy, potential energy, kinetic energy, and he gives you reasons for thinking it's not potential energy, so it must be kinetic energy. Well, if it's kinetic energy, which is producing the heat, then it's kinetic. It's energy of motion. So there must be something in motion in the fluid, in the gas. Well, we don't see anything. Gas can heat up without boiling, and you don't see anything moving. So there must be something inside the gas which is moving, something you don't see. And this kind of warms you up a bit. It gives you some reason for thinking, hey, at least Maxwell thought it did, some, as I put it, independent warrant, independent from the theory itself, from giving you for some reason to think that gases are composed of particles in motion. And the bigger the motion, the bigger the heat. All right? He also thinks, and here I would not go along with him, but he does, he thinks this is true. Look, mechanical theories, he says, have worked so well in astronomy. They have. And he says in electrical science, well, not so well. But Maxwell, of course, thought that the electric field could be understood in terms of a mechanical explanation, which he was never quite successful in giving. Okay, give him that. This is his line, that dynamical theories work well in these other areas. So he thought some maybe inductive reason to suppose that they're going to work well here. And then he finally gives a very interesting claim about mechanical explanations. He claims mechanical explanations are absolutely fundamental. And he doesn't spell out in great detail, but there's a well-known passage from Maxwell, and he says, when you can understand a phenomenon in terms of particles in motion subject to forces, then you have understood it completely. There is nothing left to understand. Okay? And it's sort of like, that's the meaning of understanding in physics. All right. So he's giving you this methodological, whatever, semantical reason for thinking that molecular theory is a good thing to have here. So that's what I call the independent warrant part of the argument, that there is some reason to think that these basic assumptions are true. Then he does what he does before. He gives you, not in the greatest detail, but he gives you what I call this theoretical development, mathematical development of the theory. But this time, he does it more in an interesting way. He says, look, I'm not going to start with any assumption about the shape of the molecules. And I'm not going to start with any assumption about that they just interact only at contact. No such thing. I'm going to take a nice equation which was proved by Clausius in the 1850s, I think. It's in a situation where you have particles, observable particles, subject to forces in a confinement, confined to a whatever. And he takes this equation, which relates the pressure and the volume and the kinetic energy of the particles to the forces between the particles. This is an equation which he then applies to the molecules in a gas. And he shows you how from this general Clausius sidereal equation, how he can derive a lot of stuff about gases. It's very interesting. He was presenting this to, I think, a more general audience, and this was a neat way to do it for him. But again, you know, it's not that he made great advances by 1875. He has these unconquered difficulties, the specific heat difficulty, the electrical conductivity of gases he can't explain. He's just got a new way of presenting these old ideas, but he also has some arguments in favor of the molecular theory, which he regards as empirical arguments, or one in terms of you know, the basic nature of mechanical explanations. Okay, so again, however, he has no proof. Okay? So he's at a sort of an intermediate stage here. He's got, he makes these speculations, method of physical speculation. It's a physical thing. He's not just giving you mathematical formulas. He's spelling it out, and he has some reason to think that his assumptions are true. Okay. So he satisfied some conditions here. He's giving you a physical understanding of the phenomena. He's spelling it out mathematically. Well, those are two conditions, spelling it out and doing so mathematically. And it gives you, again, an understanding, this time, you know, a realistic understanding from the form of this is the way how things probably are. But it's not proof. So you know, thinking about these things, I'm much more sympathetic to Feynman. Not Feynman, to Weinberg. Feynman's another matter. Feynman didn't like philosophers. Weinberg is in between there. Weinberg, I will tell you this final story. Weinberg wrote an article on scientific explanation. What can science explain? For the New York Review of Books. I don't know, a bunch of years ago. And he, in the second or third paragraphs, he said, well, you know, what do I mean by explanation? And he says, I look to the philosophers of science, and they're terrible, he says. They can't tell me. There's four exceptions. There's four exceptions that I think are okay. And you know, I felt terrific. I was one of the exceptions, he mentioned. But then I looked at the other three, all of whom I'd criticized myself, and so I was wondering, well, maybe I'm in the wrong company here. I don't know. But anyway, yeah, Weinberg is skeptical in general of philosophers. But I'm more sympathetic to where he is now, because these guys who say, you know, it's not scientific activity unless there's proof or unless there's a glimmer of how to prove this thing, unless you tell me the kinds of experiments I would need to do it, that's not science, that's speculation. Well, here you have Maxwell, and he's not giving you proof at all. He's developed this analogy, which is in 1855, which is an imaginary fluid subject to imaginary laws. In 1860, he has no experiments whatever, no empirical argument in favor of molecules, and he develops mathematically, using mathematics, he develops a bunch of theorems, including his famous, extremely important Maxwell distribution law. And then in 1875, he gives you some reasons for thinking, some empirical reasons, some methodological reasons, but again, no proof. And what strikes me is that this is perfectly okay. I mean, it's perfectly okay to work on these. It's perfectly scientific to try to figure out how gases could behave if they were going, mechanically, if we were going to explain the gas law. It's perfectly legitimate to work on this analogy that he did in 1855, but he has no theory of electricity at all. And suppose it doesn't pay off during your lifetime. Right? Suppose it doesn't. I mean, that's what Weinberg said. We're not going to get experimental proof during my lifetime, he said, of string theory. It's still a worthwhile scientific project. So, despite the eminence of William Whewell, or my characterization of William Whewell, given my characterization of William Whewell, and certainly of Hempel in the Philosophy of Natural Science book, I am more Maxwellian than I am Whewellian, or Hempelian.